Floating. Two times on the keyboard. Yes, continue. Thanks. Just check if it is charging.
Forward back. Slides. Okay. Yeah, sure. Sure. Thank you. But the mic is with me, by the way.
Yes, it's okay, but you can switch off if you like. Okay, so good afternoon and welcome to today's asset colloquium on neuromorphic and Ising computer using Spintronic domain wall devices and Spintronic oscillators. This is going to be given by Professor Debanjan Bhowmik from Department of Electrical Engineering, IIT Bombay. Before I formally introduce today's speaker, I would like to thank Professor Piyush Srivatsa, who is unfortunately couldn't be here, who actually proposed this talk. Of course, he is from STCS. To say a few words about today's speaker, as I said, he is an associate professor at the Department of Electrical Engineering, IIT Bombay. He obtained his PhD from the Department of Electrical Engineering and Computer Sciences, University of California at Berkeley, way back in 2015. And he worked in the field of nanomagnetism and spintronics for his PhD. Before he joined IIT Bombay in 2022, he actually worked for 4 years from 2017 to 21 at IIT Delhi. His current research interests are in implementing machine learning and optimization algorithms for edge computing applications through emerging devices and architectures, with specific emphasis on spintronic implementations of the same. So with this, I would like to invite today's speaker for his colloquium. Thank you.
Hey, good afternoon, everyone, and thanks for the very nice introduction. My talk today is on neuromorphic computing and Ising computing using different kind of spintronic devices like the domain wall device and spintronic oscillators. I would like to thank TIFR for calling me over for this essay colloquium. And okay, so we'll just so the talk has 5 parts, I'll say. So the 5 parts are essentially first, so you can see neuromorphic computing and Ising computing are the 2 main topics, and these are both emerging computing techniques. So some amount of motivation statement is needed for both of them. So I've spent some time talking about the motivation, and then we will first talk about what is neuromorphic computing and why we want to do neuromorphic computing. Then we'll show about some system level research, system level simulation of neuromorphic computing arrays. And that doesn't necessarily just apply for spintronic device, but can apply for various kinds of non-volatile memory technologies, including RRAM, phase-change memory, etc. Then we'll go specifically into my group's research and talk about the spintronic domain wall device and how to use it for a larger neuromorphic computing system. Then we'll talk about Ising computing, again a motivation statement, and then we'll go into more specifics about how to build Ising computers with spintronic oscillators as well as simple electronic ring oscillators, right? So Again, you can see from this that the nature of the talk is pretty interdisciplinary. So I hope I will have something for physicists, electrical engineers, and AI/ML, computer science people as well from in this talk. So why neuromorphic computing? Essentially, neuromorphic computing is a certain way of implementing AI/ML, artificial intelligence or machine learning, in a brain-inspired hardware. So the focus is still AI, but unlike the regular AI, where there is not much focus on the hardware, the assumption being that whatever algorithms you write, you implement them on a regular classical computer, be it CPU or GPU. Here, you are also innovating in terms of the hardware. So AI, the applications of AI are all around us, starting from things which you are already using, like a virtual assistant or house cleaning robot, to some futuristic applications like self-driving cars, right? So major things AI can do, out of them, I think we're all familiar by now. There are all these different complicated image data sets, and from there you can identify different objects, right? And so for that, typically use convolutional neural networks, right? And then even more fascinating, not only that, AI can also use, along with convolutional neural networks, it can use recurrent neural networks to construct sentences and give based on an image, guess a context. As you can see that based on these different images, the software can actually come up with a sentence describing what is going on this image, right? So all of this is like AI, and things are done at an algorithmic level, mathematical level, where you are essentially trying to get a mathematical framework to work with which you can do those jobs. And then the assumption is that, okay, we have great computers out there, be it servers, which are huge, or personal computers, and we are going to implement those algorithms in those systems, right? Now, but then, so CPUs and GPUs are the major runners or your major horses for running your AI/ML algorithms. Now, a large advent of AI/ML did happen in the last 10 years or so because of people were able to build these GPUs. And so it is a good hardware research indeed triggered that AI/ML. So I'm not going to say that AI/ML research is divorced from hardware research. But at the same time, the hardware has stopped in context of AI/ML only at GPUs, the innovation level from going from CPUs to GPUs. Now, what neuromorphic computing tries to do is tries to take inspiration from the brain and inspiration from how neurons are wired in the brain to come up with some more novel hardware architectures so that the AI/ML implementations can be more efficient, right? So if you look at what is leading to that inefficiency for AI/ML on a regular hardware, is that when these hardware people, the hardware innovations were done in connection to a regular computer, be it CPU or GPU, it was always built on a memory computing separation. So in a CPU, you will have one memory, and on a computer completely separate, the processing completely separate. GPUs will have many cores, but within each core, you will still have this memory computing separation. So you essentially have so this memory is separate from the processor, and the memory can be on chip as well as off chip, right? So if you are buying a computer in a computer that you use, you will have in the processor chip there is some amount of cache memory, and outside it you have the main memory, which is a standardized memory chip. And what happens is when you try to run the regular AI/ML algorithms on this kind of hardware, you spend a lot of, so it involves a lot of matrix elements, tuning up those matrix elements, changing them, updating their values and all. And that involves a lot of information exchange between your memory and your processor. And that leads to a lot of energy consumption in that bus, right? And speed also gets affected. So that is called the von Neumann bottleneck. So what von Neumann architecture essentially is the idea of memory computing separation to make the computer general purpose. So which is a great thing, but what is a great thing, which is the von Neumann architecture, also ends up becoming some sort of a disadvantage or some sort of a limitation, and in the form of the von Neumann bottleneck. So what neuromorphic computing typically wants to do is tries to take inspiration from the way the neurons are connected to each other through synapses in the brain, and try to come up with some kind of a hardware which mimics that to some degree. Now the level of mimicking varies. Sometimes you are just having this kind of a crossbars, like you can see on the bottom. So at the bottom you can see that these are these crossbar structures. I will show those crossbars in more details. And so in these crossbars, they are kind of inspired by how neurons are connected to each other through synapses in the brain, right? And apart from that, the neurons typically in the brain communicate information in the form of spikes. So in this neuromorphic computers, typical people, unlike using floating point numbers in a regular AI/ML systems, here in the neuromorphic systems, people tend to work with spikes. So these are the major brain inspirations that a neuromorphic hardware typically has. So if you look at the neuromorphic hardware, so you can see that there is still some amount of resemblance with the regular one-dimensional computer architecture that we showed, because you still have to make a general purpose. But at the heart of this neuromorphic, you have this compute in memory cores, where essentially those compute in memory cores can be thought of like some kind of a crossbar arrays. Like as you can see here, these are the crossbar arrays. So these blue boxes are essentially non-volatile memory elements. And when I talk about Spintronic devices, those will come in as those blue boxes. Instead of that, you can have RRAM device, ferroelectric device, phase-change memory device, other kind of material devices. But essentially, you are using the non-volatility property of those devices. And then, so if you have this kind of an array of memory device, like non-volatile elements, that's typically a memory. But then when you can add some amount of computation aspect to it, then it becomes compute in memory, and some people will call it neuromorphic computing because of the brain inspiration, right? So we largely work on this kind of a crossbar array system modeling, and then thinking about what devices you can build and what are the typical things that you need from those devices, such that this computing in memory computing platform works well. So the major advantage of that essentially is in AI or ML, when you're trying to train these neural networks, there's a lot of matrix vector multiplication that you need to do, and you have to update a lot of these matrix elements, and those things can happen parallelly in this kind of a compute in memory core systems. So you can have many CIM cores interacting with each other, like you can see, and together you are forming the system, right? So what we'll do next, okay, I'll just, yeah. Sure.
So is this the network that you'll be using? The network architecture is the same?
Yeah.
It's not more complicated. It's a 2D grid.
Yeah, mostly, yeah.
Nearest neighbors join.
Yes.
And the weights are being
updated. Yeah. That is the main. There can be complicated peripheral circuits around it to communicate and all, but the major advantage is coming from this code itself. Some people will do some more extra things, like instead of like in a regular computer you're using floating point numbers, but then some people don't use. I know the topology is same, but I'm saying that we'll still use floating point numbers here, while some people do an extra layer of innovation that the information manipulation there, instead of using floating point numbers, they use spikes as a brain inspiration. So that is another degree of brain inspiration which you're not really focusing on here. Okay, yeah, but this is the main hardware structure. Okay, and in terms of the applications, so question is, yeah.
You're limiting yourself to this because of fabrication problems, or because you find it easier to
limit to what?
This topology.
Yeah, because this is like again, we have to standardize it somewhere. So this is called the crossbar architecture or computing in memory architecture, and a lot of work shows that this can actually really accelerate your AI/ML like algorithm running. So, and the thing is, it's very friendly with the kind of hardware we work on, because those blue boxes that we showed, these are essentially memory elements, but unlike storing just zeros and ones, they will store many analog values in between, and the devices that we work on largely are friendly to that. So for all these reasons, we are kind of sticking to the architecture. Some amount of hardware motivation, some amount of computer science motivation is there, and some amount of our hardware limitation also there. So both together kind of have made us converge on that. Okay, but there are other neuromorphic groups we are doing even more exotic stuff compared to that. So application-wise, word we are going to use neuromorphic computing. Now here it's a bit of a problem, because neuromorphic computing research has been going on for a long time, from the 90s and all. Again, it is like of a somewhere where there is a solution, but what is the actual application space of the solution? That is itself a major debatable thing. So it looks like the problem with the neuromorphic computers compared to the regular AI ML on GPU is that the precision level is much lower, and so the accuracy is not that high. And if you are trying to train a very large system like these large language models like ChatGPT and all, this is not going to work, right? So where people are trying to sell this neuromorphic system is like for edge devices like robotics or edge healthcare. So there what happens is in like robotics, if you want to take signals from the human body, different kind of signals, and then you want to manipulate them, do some kind of signal processing with that. Or in so edge healthcare, right, where you have EEG, ECOG, these different kind of signals, and then you want to put some electronics within the human body itself, along with the human body, where you are processing them and doing something intelligent with it. So in those kind of cases, sending that data to a regular computer, doing this computation there, and then bringing it back to the edge, that is not very efficient. So when it comes to edge computing, this is where the main application of neuromorphic is evolving, right? So again, this is something that is going on. Yeah. Edge computing means, so it's like, yeah, EDGE, edge. So edge computing is like, so suppose if you have, suppose on these lights and all, when the people are not there, the lights turn off. Yeah. Distributed computing, where the computation is happening close to this, where you're detecting the signals. So that is what people are trying to think of neuromorphic, because these are typically they consume a very low amount of energy, and where the energy budget is tight, there you end up having this, right? This can be of advantage. So that is, again, we are attending a lot of neuromorphic conferences where people are still brainstorming about where exactly can they put it to use, right? So now coming to our group's research, again, we are working on another 40 minutes. Right? Okay, that's fine. Then I can go slow. Okay, so in our group, we are, as I said, I will try to, like people from the CS department as well as people from the physics and material science departments, I will try to have something for everyone. So the more CS side of our research, I will first focus on, and this will give a general framework of what kind of capability our neuromorphic system we are being able to show, and what kind of a hardware requirement we need, right? So at that point, the physics becomes not primary. What the requirement that I have from my machine, that becomes primary, and based on as it will evolve, you will see that what exactly kind of physical devices will be needed, right? So as I said, at the heart of this whole neuromorphic computing is this computing memory CIM architectures or crossbar architectures. So here what happens is you have this horizontal lines and then these vertical lines. Now they cannot be on the same plane. It has to be on a 3D structure. And these blue boxes are some things which like vias which are going in between the horizontal and the vertical things. The major advantage here is these blue boxes are essentially elements whose conductances you can tune, right? So imagine it's like a potentiometer where by moving a knob you are changing the conductance values, right? So you can map the weights of your neural network to the conductance values of these blue boxes, and then when you apply a signal, input signal, the vector matrix multiplication, which happens all the time in neural networks, that can happen at one go in a crossbar array like this. So that is the major advantage which people cite of using this kind of crossbar arrays in neural network implementation for AI/ML, because today's AI is mostly neural network, and this big multiplications can happen at one shot in this kind of a crossbar array, right? Apart from that, there are some additional advantages. One is the fact is not only you have to do the forward computation when you are doing this weight input multiplication, but you need to update the weights as well. And those weight updates can also happen simultaneously if you use this architecture properly. And as I showed, these red lines are control lines through which the weight will get updated. Yeah, so these red lines are control lines through which the weights get updated. Like you pass a signal and you update the conductance values of these blue boxes, and they can happen in parallel. So you can use this kind of crossbar arrays or these neuromorphic systems in two modes. for edge computing. One is
EMM.
then
What is the model? What is
The model, the matrix is distributed in the crossbar
yes, the blue boxes contain the matrix elements. in the
matrix
form of
elements,
conductors.
and the inputs are coming from one end of the
Yeah. Yeah.
crossbar and read out at the other end.
Yeah, you read out at the other end.
Mhm.
Then if you have to do this nonlinear activation functions like ReLU and sigmoid and all, you can either do it digitally or you can build analog circuits to do it, and then
So-
you pass it to the next layer.
So every edge in your graph is a nonlinear element.
Every blue box, these are a nonlinear. All these Fs.
F's are
okay.
nonlinear
Nonlinear.
elements, and the edges are
Which edges?
edges. No, the lines of the lines joining the blue boxes.
Okay. So essentially it's a horizontal line like this, and there's a set of lines. These are like voltage lines. Okay. You can imagine like you have a set of lines like this, and then vertically there's another set of lines. So we apply voltages, and the currents flow in these blue boxes. The currents add up flow through Kirchhoff's current law, and that is how you do the VM.
So those are just passive wires.
Yeah, passive bars. Yeah.
That's basically managing some kind of current summary,
Mm-hmm.
which is weighted by the conductivity of
Oh,
it. So
yeah.
each node is taking some V input,
Yeah.
divide by R. So
Yeah,
that's the
yeah,
current.
yeah.
So the next step is
Yeah.
another current, and then
Yeah.
all of that gets added.
Yeah.
So that's why you're calling it a matrix.
Yeah. So each one of our R element is proportional to one scalar element of the weight matrix, basically.
This is your input column.
Yeah,
and
yeah,
capture output
yeah.
column.
So one advantage comes from the fact that you can do the forward computation. Another advantage comes if you can update all those weight elements at once, right? All these blue boxes, if I can pass the right kind of signals and update them at once, then that is another advantage. Your training also becomes fast.
So and you can do that,
Mhm.
and you can do that fast.
Hmm.
You can change the matrix fast.
Yeah, you can do both. Okay. So that way, people are thinking of two ways of using it. One way is you don't. So in a machine learning or AI, there are two aspects to this. One is you train the neural network, and then you just test the neural network. So some people argue that we don't need to train the neural networks at the edge. We will just feed the data to a regular computer, train the neural network on my regular computer, bring those weights to the crossbar arrays at the edge, and I'm just going to do inference at the edge. In that case, only this left side is all that matters, the vector matrix multiplication. You don't need to update these weights. And then there's some people argue that we are not going to send the data from the edge to the central computer because that will affect your privacy issues and all that. We will train it on the edge itself. So in that case, you need to have a capability of updating the conductance elements at the edge itself. Then that is more challenging.
I'm thinking of a application which has nothing to do with what you're saying, but just a large, large computing
Right.
problem, which is exactly VMM.
Mhm.
Okay. So how large can you make these arrays? These are on chip, right?
Yeah.
There's one chip which will do this.
So it depends upon what technology you use. My technology that I use, people have not been able to yet make huge crossbars. But if you go by this RDAM technology, resistive RAM technology, there people have made pretty huge crossbars. I can give you the exact numbers, but it should be pretty
Like
big.
million by million? Or?
Yeah, something like that. Yeah, but that is for the resistive RAM technology. That is, there are even some small startups also now which have started, which can build this kind of a crossbar arrays.
So that's the reason I asked this question is because this is a basic step in quantum field theory calculation.
Okay. Now, if you already know what the elements are going to be for this matrix, then it's easier. But if you don't, then it's even more challenging.
No, those also have to be updated very
Yes,
rapidly.
that becomes more challenging. That I don't know whether capability is there in this million by million crossbars or not. That might not be there, right? The updating capability. Right. Okay. So so if we focus on the second aspect, which we wanted to emphasize on our group, we try to do both. Then we need some additional properties from these blue boxes compared to what I need on the left case, right? So anyway, what are the properties that those blue boxes need to have, right? So they need to store multiple conductance states. If they're just storing zeros and ones, and so the difference between a neuromorphic, one of the differences between neuromorphic computer and a regular computer memory is that in the regular computer, the memory, each element is just storing a bit, 0 or 1. And if you want to do it that way, your weights can only be zeros and ones. And so then you need a huge arrays to do that. So ideally, you would want every device to be able to store a lots of possible values of weight. So multiple conductor states it should store. The higher the bit resolution go to, the better it is. Electrical readout has to be easy. Like if you apply a voltage, a current has to flow, and that current has to be sufficient. If it is not a lot, then you all the calculations are going to be wrong. The another thing is non-volatility. That is very important, right? You store your weight values in your crossbar. If the weight values go away, the weight values get corrupted, then the training is not useful anymore, right? So those three things you need to have, whether you do on-chip inference, which is just testing the network on the edge, or on-chip learning, where they're trying to learn on the edge also. The fourth property is more important when you want to update those weight elements on the edge. There, in that case, you need to have a very smooth and linear control over this. Like you apply programming pulses. So if you go back on the last slide, through these red lines, you are applying programming pulses, and very smoothly the weights are updated. So if you also have that property, then that is even better. So question is how to do that, right? And so what we have tried to do in our group from a machine learning perspective or a computer science perspective, we have tried to build large simulators which will do behavioral level simulations where I can feed this kind of properties of these elements, like of these blue boxes. I can give very ideal properties like this, or I can give deviations from that, and then my simulator will be able to predict how much accuracy I'm going to obtain, right? So I'm not going to go through all the details of that because I have a lot to cover. So I think this stuff is standard in regular neural networks, and also these are like different network topologies. This is the fully connected network. Then I will show more complicated stuff like convolutional neural network. But either way, we suppose we have just taken made different kind of assumptions with these devices, and then seen which one is most critical, right? So most of the results that we get are obvious. So I'm going to quickly go over it. If the weight update property is very linear, that is, it goes up very smoothly up, very smoothly down, comes down very smoothly, then is very good. Even then, we need at least 4 to 5 bits. Like each device should be storing at least 4 to 5 bits. That is, must have 30 to 40 levels. Like 4 bit is 16, 5 bit is 32, right? It needs to have at least 16 to 32 levels in order for you to do any kind of a train it on for any meaningful task. So what I'm trying to say is these blue boxes, if they have conductance levels, they cannot be ones and zeros. If they are ones and zeros, you need a lot of devices. So each device should have at least like 30 levels, so which is like 5 bits. So can we make a non-volatile element which will have 30 levels, right? So that is a challenge for a materials person, say. The next challenge is linearity. So what happens is all these devices, whether it is RRAM, phase-change memory, Spintronic that we'll talk about, you apply programming pulses and we're gradually trying to tune the weights. And there is some inherent physical mechanism in the device which leads to this conductance tuning or the weight tuning, right? But the inherent the physical process will be such that it is not going to be like a very smooth going up and very smooth going down of conductances. It will deviate from your ideal behavior, and the more the deviation, the worse it is. So we have done some kind of a system level simulation to find out up to how much of deviation can be tolerated, and again the results are fairly intuitive that these non-linearity factors that right 1, 2, 3, 4 are essentially a way to benchmark the deviations, and up to a factor of 3 non-linearity factor it is okay, beyond that is not okay. And some more stuff we comment on asymmetry, which I'm skipping. Yeah, sure.
Your updation
protocol
that you have used,
Mm-hmm.
Protocol that you have used,
Mm-hmm.
does it depend on the initial state, like the memory effect, or does it depend on the actual voltage? Basically, if I put a 1 volt, all of them goes to a particular state, or it depends on which states they are already in, they're just moving up to the next step.
So what we do is, see, if you in a regular computer, the weights can be at any value and you can take it to any other value. We're just updating weight,
Right,
you don't
but
care
I
about
thought you had a single line, you want to
Here
update
they-
all of them
yeah.
together.
In here, what we do is you start from any arbitrary values of weights.
Mhm.
All the elements are at arbitrary values of weights, and the way you train it is at every iteration you just make the weights go up by 1 level. You can make it go up by more levels, but that makes the circuit complicated. Like the update.
You're assuming like they are just going from
Yeah.
initial like the
Yeah.
state I to state I plus
I
1.
plus 1 or I
Okay.
minus 1 or stays at the same state. Essentially, you are at some random values of weights. From there, you have to go to the correct values of weights. But while you are going, you are limiting the trajectory that I cannot jump more than one step at a time. That makes your control circuit simple. And with that limitation, whatever I'm showing all the results. Okay.
Yes.
So that we are putting that. So initially 5 or 10 years back, it was that itself was the challenge, that can neural networks train if I limit the weight update to just 1 bit? As it turns out, yes, for most cases, right? And then this is another study which is again very important from engineering perspective, is when you are talking about millions and millions of elements, right? Say 1,000 by 1,000 crossbar or something. These million synaptic devices are not going to be identical. They are going to be variations. So device to device variations. And as you update the different update cycles, there will be variations. How much deviation can it tolerate? So we have done those kind of calibrations as well over here on the system. Overall big picture, I think we can say that if a device had at least 5 bits, that's good. And even then, when I try to do convolution neural network, so far the results were for fully connected neural networks, which are very simple. On the other hand, when it comes to convolution neural networks, which is the state of the art, these are problematic stuff. Like there, when the weight update is just 1 bit, the network doesn't train very well. The weight update has to be at least 4 or 5 bits. And then there you need to have like about 15 bits of per weight. Like each element of the crossbar needs to have like 15 bits. And most of the technologies that we have so far, the device having 2 to the power 15 levels is very, very hard. So what people typically do, they use 3 devices, one for LSB, one for middle bits, one for the highest bits. That's how they do it, right? So we have done this kind of system level study. Now we'll come to what is the device we are working on, right? So the system level study that we did applies to a large kind of technologies. It should be applicable to any technology, memory technology, which is non-volatile. Like where you can update your weights and the weights stay where it is after you have done your update. So that would include resistive RAM, that would include phase change material, that will include ferroelectric, that will use Spintronic. Based on my research background, I have chosen to do it as Spintronic, but there are other people who can do ferroelectric and RRAM, etc. kind of devices and still be able to use that system level analysis. So now we'll come to the device level work. We are focused on the Spintronic device, which is so now different. So again, all of this RRAM, phase change, Spintronic, when you are using it as a neuromorphic technology, is just an extension of them being used in the memory technology. Already people have been thinking and have been using them for building memory chips. The difference between that and neuromorphic is in memory, each of your device will have just a 0 or a 1. On the other hand, each of this device will have many levels between 0 and 1. Okay. So question is, in RRAM people have been able to do it. In phase change people have been able to do it. In Spintronic, is it possible to have multiple levels between a 0 or a 1? So in a Spintronic device, like an STT-MRAM or an spin-orbit torque MRAM, the way you store 0 and 1 is you have a ferromagnetic layer which you limit when you make a device of a 30 nanometer device or something. Inside that, the magnetization is uniform throughout. And if it is vertically up, you call it a bit 0. If it's a vertical down, you call it bit 1. And you apply in a spin-orbit torque SOT-MRAM, you apply current through heavy metal. The heavy metal has a very high spin Hall effect. So you have spin polarized electrons generated in the interface and the magnet switches, right? So that is if you want to use it as binary device. But if you want to use it as this kind of a multi-bit resolution device, then what you need to do is you need to have a way of creating magnetic configurations in the device such that some of the moments are up, some of the moments are down, and you can control how many moments are up versus how many moments are down. So that is being done using this, domain wall. As you can see, this green structure in between, that is the domain wall. Okay, so that green structure that you're seeing here, that is the domain wall. And then when you pass current through the heavy metal, because of spin orbit torque, the domain wall moves. Domain wall moving means nothing more than the magnets switching in a particular fashion, right? So if these domain walls move all the way from left to right, if the domain wall is at the left edge, all the moments in the ferromagnetic layer in which the domain wall moves, these are up. When the domain wall is at the other end, all the moments are down. And because you have an MTJ structure at the top, so the conductance of the device will change from a very low value to a very high value. Okay, so if this part is clear, I think rest of the things follow. So what we have done is this work has been done in myself and Professor Pranab Mudil in physics in IIT Delhi. So we have grown this kind of a through magnetron sputtering. We have grown this kind of structures: tantalum 2, platinum 5, cobalt 1 nano 1.2, SiO2 1 nanometer, platinum 1 nanometer. So this structure, in this structure, the platinum is the heavy metal, which is your source of a spin orbit torque, and cobalt is the ferromagnetic metal in which your domain world moves, right? So we first characterized these thin films in SQUID VSM, and we got a nice out of plane loop for which is showing perpendicular magnetic anisotropy. There's a magnet which is very sharp. So getting PMA or perpendicular magnetic anisotropy itself is a challenge. Unless you have a very good material system, like a growth system, you are not going to get PMA. Okay, so you got the perpendicular magnetic anisotropy. What PMA enables is that the magnetic moments can be vertically up or vertically down. That is the low energy configuration, right? So then what we did is we made Hallbar devices, which are like 20 by 5 micron, 20 by 10 microns Hallbar devices. Apply current from one direction, and then measure voltage in the vertical direction. And you can see the ratio of the measured voltage to the rate current is the anomalous Hall resistance, which is proportional to the outer plane magnetization. So essentially, the moments can be vertically up, or the moments can be vertically down, or the moments can be somewhere in between, some up, some down. And where it is, we can measure through this anomalous Hall effect. Okay, and what we see is that, so for reading, I am using a small amount of current, but for writing, which is basically manipulating the magnetic moments, I apply a much larger magnetic write current value. And because of that high write current magnitude, what happens is the moments switch down from up if the magnetic field is in one way. If the magnetic field is in the other way, the moments switch from up down to up, and other way it is down up to down. So this is the signature of spin orbit torque based switching. And people in the Spintronics community, if they see this kind of a switching where the handedness of the curve reverses based on reversing the direction of in-plane magnetic field, they know that this is spin orbit torque driven magnetic switching happening because of the high spin Hall effect in your heavy metal. Okay, so this is switching data, but what is really important is being able to get mixed states or cis states with magnetic configurations pretty arbitrary, and so that you can get those intermediate conductor states, right? So that is what you have been able to do experimentally. We apply pulses, and this programming, based on this programming pulses, you see the anomalous Hall resistance gradually changes. It gradually goes up, and then when the pulses are negative, you can see that the anomalous Hall resistance goes down. So essentially, the anomalous Hall resistance is proportional to the average outer plane magnetization. So outer plane magnetization, starting from all vertically down, it gradually goes all vertically up, and similarly it goes further down. So from a neuromorphic perspective, what is of interest is how many states do I have and how many states can I reliably go to? Because the more states I can reliably go to, more distinguishable states I can reliably go to, and the more stable they are, I can store many weight values on those boxes. So end of the day, those weight values are represented as conductances. Conductors multiplied by current will become your voltage, and the voltages will, voltage multiplied by conductance will become your current. All the currents will get added up. So if you have more and more stable states here, then is better it is. And what we did show is that we took certain number of states, some states here, prepared them again, and made them stable. And 600 seconds is like what, 10 minutes? We actually went longer than that too, and we saw they're kind of stable. We measured the fluctuation, and if the fluctuation is less, one order less than the difference between two consecutive states, then we considered those states to be stable. And that we found about 30 states, so about 5 bits per synapse device. Now then we applied some kind of a pulse stream, changed the pulse stream a bit, and then from 32 to 64. One obvious one is increase the size of the device, and then the domain will move more, but then that is not a scalable technology. So multiple ways you can do it. One is you can play with the programming current pulse magnitudes, and if you can tune the current pulses such that you can make the domain well move a bit more precisely, you can increase the number of levels. But again, the problem is how far you can go. We did some scaling studies, and we realized that to get to 32 or 64 or some high level levels, the device length has to be like a micron, which is itself not good. And then what people will do, like somebody working on more exotic materials will try to think of how to make a even more thinner domain wall, or go to some other kind of topology structure like skyrmions or something. So that is where the innovations can happen, because
This is more or less currently.
yeah, that because these domain wall devices, we in the papers when people have asked to do a scaling study, we realized that if you have to have 6 levels, say, then you have to have like a micron device, because each domain wall is like a 50 nanometer width, and you can precisely detect domain wall motion every 50 nanometer. So 50 nanometer times 64 is like already you are in the micron scale, right? Then, but if somebody can say that I will have one nanometer skyrmions, and I'm moving this 1 nanometer skyrmions on this chain, then suddenly that 1 micron will become 100 nanometer. You see, that is what the innovations are. Yeah, it is something on which people are writing papers basically. So
Yes.
yeah.
Currently, there is only one domain wall. I mean, there could be multiple domain walls.
Okay, so that's the thing. So we have so we'll have a better answer to that later. So I'll tell you what is it. Our group at this moment, when we did the experiment, we did not have the capability of measuring magneto-optic Card effect microscope images. But there are other groups which have, while showing this kind of states, been able to do more imaging and shown that there is only one domain wall which is moving. And currently we are building up, we have now got the facility now that while we measure the states, we can actually image that system. Then we will be able to give you a convincing. For now, the way we have got the paper is we showed this device and we explained it through a simulation which is showing a one domain wall moving. But yeah, based on this data, there is no guarantee that there is only one domain. Okay, there is some kind of leap of faith which we took. Yeah. Okay.
Feature scheme, I saw that the blue boxes were attached by a single red line.
Yeah.
So when you write now, you are going to write the whole of the line and say how many. So, how do you address a single unit?
Yeah. So that's a very good question. So the thing is, the blue boxes, well, so we had given quite a thought to it, and we had, if you are just using it not to update the weight, just you have the final values of the weight, so you have these devices at the domain walls at the precise positions, you're not updating them again. The blue box being just the domain wall device is sufficient. But then if you want to update the device, you are very right, that if the same pulse goes to all of them, they will all update by the same value, but we want them to update by different values. So what we have done is, you can read one of our earlier papers from 2020, where we have a scheme. First of all, we have simplified the training algorithm, limited the weight update just 1 bit. What we did is, we basically showed something like this. I will tell you. So inside each blue box, you not only have a domain wall device, but you have two transistors which act like a bit by bit multiplier, like multiplies 1 bit with 1 bit. So what happens is, you can see here, based on what you calculate here, so ultimately the weight update at each synapse in the neural network can be written as a product of the input and some kind of a thing you calculate from here. So what you calculate from here is common across all the devices, and the inputs are different to each of these devices. So you need to have a couple of transistors to do a multiplication between those two, and then the signal coming out of the transistor, that is what you have to fit to the domain wall device. The device alone, yes, then all will update with the same value, then you will never train it. So in one sentence, if you are just doing inference, the domain wall device alone is sufficient for a blue box. If you are trying to have an on-chip learning capability, no. You need to have a small multiplier along with the domain wall device. So there are more details in the papers. Yeah. Yeah.
Just if you go back to that image, just
Yeah.
following up on that, I mean, isn't this a standard problem in any RAM kind of thing? I mean, you just need another set of horizontal wires so that you can address each box uniquely with two numbers.
No, but in the RAM, you update elements one by one, right? See, in a regular memory,
Yeah.
when you're writing,
Oh, you want to
don't fit
update,
parallel. Yeah,
you
don't
want to
fit
update
parallel.
them in parallel.
What they do is they give a bit string, and that bit string gets converted through a decoder into some channels are you can
Yes.
reading or writing only one at a time.
Yes.
But if you do that here, it is very slow. The whole advantage will come only if you can update all of them at once. And for that, you need all these extra things that we thought of. I mean, a lot of this is kind of honest imagination at this point, because our device, we have just like one device or like 10 devices. But if you can build like at least even 10 devices in a 3x3 array with transistors, and you can show that update happening parallelly, that's pretty big, I guess. In memory sticks, people have tried.
Even in other technologies for making neuromorphic, this has not been done.
No, it has been done. In memory sticks, people have done it. RRAM, people have done it. So Spintronic technology is way behind the RRAM technology in that scale. A lot of reason, one reason being RRAM is easier, I guess, to fabricate. And also people started doing these things in RRAM a long time ago. While in Spintronic, people have only started doing it now, right? But in RRAM, people have tried to
Yeah.
build this capability.
Sorry, now that Vijay brought you back, I had this question like when you proposed the crossbar architecture. So, I mean, the whole paradigm is supposed to be something which inspired by biological systems. So, I mean, is that analogous to anywhere the way that you design a crossbar? Is it analogous in some way of the information processing in biological systems?
Yes and no, because what happens in the biological in the brain, say, I had some pictures for this too. Yeah. So what happens is there you have a mesh of neurons connected to each other through this synapses, right? So here also similarly you have an idea that you'll have these horizontal lines and vertical lines which will be crisscrossed through these devices, right? But the differences are, that is the only similarity. The problem with the difference is that in a biological system, your neurons can coil like this, and like each neuron is connected to 10 to the power 4 other neurons because it's like a coil, right? Like on the other hand, in solid state systems, you can do like what? Like horizontally, vertically, maybe you can go 3D, but still 3 directions, right? Not like 1,000 directions at once, right? So that is the major challenge. Like the kind of getting the kind of connectivity that is there in the neurons in the brain, trying to get it on hardware is a major challenge because you can only get a much limited connectivity, right? So I'll quickly finish this domain-wide device part and come to the oscillator part because I wanted to show that one. That is what I guess the overlap with the quantum computing is there. So I will just quickly finish this up. I think I've carried home the point that we have made some devices which satisfy this, and rest of this is just benchmarking. Imagine I had like thousands of these devices made in the lab. How would that perform? How would that compare against other devices? And there we showed that, you know, our devices were pretty comparable to many of the other technologies like RRAM and electro. So our Spintronic device technologies are the last one. The others are with Fed Electric and electrochemical RAM and RRAM and all that. And so what we said as our device is pretty comparable to them. But then in those other technologies, in many of them, particularly RRAM, people have built huge crossbars. Here, nobody has been able to do it thus far. And in terms of energy and speed, we did some computation calculations, and we did show that, you know, in terms of speed, we have a major advantage as given by this total time for training, as well as the top one is for training for time for inference, while this is time for training. That's why these orders of magnitude higher than that. But we can see that Spintronic is really, really fast. Okay. And in terms of energy, Spintronic also does pretty well, but still it is ferroelectric tunnel junction is probably the most energy saving technology, because in Spintronic, you still need to pass current to do the writing. On the other hand, ferroelectric is about electric fields. So on the insulator, you are just charging up the insulator and all, so that is even more energy saving, right? Now, coming to Ising computing, I will try to do it fast. So the thing is, just like neuromorphic computing was edge computing to solve machine learning problems, Ising computing is more like edge computing to solve optimization problems. Okay, so you want to have some kind of a customized hardware which is meant to solve optimization problems, and typically these optimization problems are NP hard in nature. So as in, or if you try to solve it on a regular computer, it will consume exponential time to get to the correct solution. And some of the practical applications are like traveling salesman problem, then airline crew pairing, and then all these different kind of drug discovery, protein folding, etc. So there are different kind of optimization problems keep appearing here, right? So one of the ideas to solve optimization problem is Ising computing, and the D-based quantum annealing is also, you know, a particular way of doing Ising computing. So essentially what you do is you convert the optimization problem into the Hamiltonian of a system, physical system. You think that if you have built a physical system, the Hamiltonian represents the problem landscape, and then you try to go to the ground state of that Hamiltonian in some way, right? So there are different ways people have tried to go to the ground state, and based on that, you have these different techniques of solving this problem. One of them is called classical simulated annealing, where simply you go to the ground state, but you are in a particular state, you calculate the energy difference between that state and the next state, and then you have some kind of algorithm to go to the ground state. So you write an algorithm on a regular computer and you go to the ground state. So that is a classical simulated annealing, and these people have tried to come up with these probabilistic computers, and even like on FPGAs, and I don't understand much about that, but they're trying to implement that classical simulated annealing or some kind of a customized hardware. That is one way of doing it. The other way of doing it is quantum annealing, which is what D-Wave does, and that is they convert the problem into a set of qubits and let the system evolve till it gets to the ground state. And there is the main claim that they make is that if you are trying to do classical simulated annealing to go to the ground state, and imagine you have like two energy levels like this, like you are trying to go to the lower level from the higher level, you have to go over the energy barrier. But in quantum annealing, you can go through the energy barrier using some quantum tunneling. Now again, that claim is like from whatever I've read, it is like that works for specific problems. Like in quantum annealing, they have taken particular set of problems where the Hamiltonian is such that there is some kind of short barrier between two minima, and that tunneling thing works. But whether that is universally applicable or not, I don't know much. But others here in the audience probably can comment. So quantum annealing tries to use that tunneling thing, and as you can see, is one of these papers is actually depicting it, this tunneling thing. Okay, again, but that works only for some specific set of problems. And then QAA, quantum approximate optimization algorithm, is a gate-based version of the quantum annealing, where some of the computation happens, the forward computation happens in the quantum circuit, and the optimization itself happens in a classical computer by just running an optimization algorithm on a regular computer and going, trying to optimize that function. Third one is the oscillator-based systems, which is going to be the focus of what I'm going to talk about. And in this oscillator-based systems, what happens? You have an interacting system of oscillators, and starting from some kind of a state, you lead the edge, these oscillators evolve, and the hope is the final state the oscillators reach, the phases of those will essentially give the solutions to the problem. All right. So these are the three different approaches largely in which you can separate this, right? And to compete with all this, there is this classical optimization algorithms like the Gibbons-Williamson algorithm, which are there's a semi-definite programming technique with which people can run those approximation algorithms on a regular computer and get to the solve the problem. So there is nothing necessarily as going to the ground state of the Hamiltonian, but some alternative way of solving the problem. So I will just tell you what the big picture is. Again, there is something for computer scientists and something for physicists and engineers also in this. So we have the oscillator-based system. First, we are not thinking about the hardware at this moment. First, in the first initial result, it is more like just at algorithmic level solving the oscillator dynamics through this Kuromoto model of oscillators and trying to see whether it can indeed, imagining that there is a physical hardware, can it really, if they follow these equations, imagining that my physical hardware will follow these equations, can I actually get to the ground state? And I see it through simulation. So we did that kind of stuff, and I'll come to those results also. But additionally, we thought about how to implement those systems with actual physical oscillators. So first, I will show a fancy one which we have simulated, and then I will show a cheap one which we have made. The fancy one is with Spintronic oscillators. It's fancy because it works at a very high frequency. It works with nano size dimensions. It consumes very low energy. And our macromagnetic simulations show where we are solving for the magnetic dynamics of this oscillator systems that show that you can take these oscillator systems and the way the magnetic moments, when in this spin oscillators, what happens earlier, passing of current through the heavy metal led to spin orbit torque and led to magnet switching. But then the spin orbit torque can be tuned to a point where instead of magnet switching, the magnet can be driven into a setup, then into an oscillation. So each of these oscillators, the magnet is driven into an oscillation. And then when the multiple oscillators sitting next to each other, through electromagnetic waves or through spin waves, different ways they can couple. Here I am showing electromagnetic wave or dipole field based coupling. Okay. And what we show is this coupled spin oscillator system follows the previous equations, this Kuromoto model, which basically means my coupled spin oscillator system will be capable of solving this kind of optimization problems. And then I'm comparing that for benchmarking, as I said, with this classical optimization algorithm called Gibbons-Williamson algorithm. And I'm also comparing it against QAA, which is a gate-based approximation of the quantum annealing problem. And what we do see is, again, at a pure simulation level, we have taken different kind of graphs. So it's very important. We have tried to solve the max cut problem, which is basically about, just going by the slide. The max cut problem is about, okay, wait, yeah. I have given an example of max cut solution here in the graph. So given a graph, your task is to partition the graph into like two pairs of nodes such that the number of edges which connects members of one pair with members of the other pair is maximized. Okay, and you can see this is the 8-node Mobius ladder, where intuitively you would probably think that I'll go for alternate nodes and that will be the max cut, but no, there's some other solution. But still Mobius ladder follows a certain pattern. Once I go to this graphs, then there is no known solution as such, because once the graphs, we have tried different kind of graphs like random cubic, Erdős Rönui, weighted complete. So the first two graphs, one node is connected to three other nodes, is not, it's very sparse. On the other hand, every node is almost connected to almost half the other nodes in the graph. So these are much more dense. Okay, so for all these graphs, we have tried to solve this thing. And the thing is, beyond this, if you try to solve it on a regular computer, solve these problems on a regular computer through a brute force algorithm, accurate algorithm, the computers, you can't simply solve the problem. Like 20 node graph, if you try to solve it accurately by doing brute force partitioning, it simply cannot solve. So to solve it on a regular computer, you use some kind of approximate algorithm like GW, which runs really fast. And then we're comparing it with simulation of this oscillator system, as well as a Qiskit-based simulation of QAA, quantum approximate optimization algorithm. And what we did show is that GW does really well, which is a classical thing at the standard industry benchmark. The oscillator systems are able to catch up with it. QAA is falling quite behind the quantum and QAA, but quantum annealing, surprisingly, even at experimental level on D wave, does pretty good actually, for some reason which I'm not very sure of. But anyway, the oscillator systems do pretty well, and this is an important result which talks about the time to solution, like how much time it takes to solve. And there what we show here is the GW algorithm, the time to solution goes up. In the oscillator system, up to 20 nodes at least, it is not really going up. But we have tried to go to larger nodes and have seen that if the edge connectivity is bad, like there's a lot of connectivity, then even here in the oscillator system, it goes. So it's kind of a debatable whether the oscillator system is better than the GW or not, but it is definitely doing better than the quantum QAA system. Okay, and then we tried to, again, building spintronic oscillators and try to show the coupling in them and all experimental is pretty difficult. So we have a poor person solution to that, which is using electronic ring oscillators. This can be done by making a proper analog chip and all, but that is more fancy. What we did was something very simple. You just take a hex inverter chips, and each inverter chip will have 6 inverters like this. So we use 6 inverters from here and then 3 inverters from the next one, just wire them up together in a loop. And this is essentially an oscillator at like some megahertz, 1 megahertz or 2 megahertz at some frequency. And then multiple oscillators can be connected by putting resistive elements between the inverter gates. So we did that. So these are my coupling elements. So essentially these are the nodes of the graph and these are the coupling elements, these blue boxes. And we were able to solve, and here you look at the phases of the oscillators, just like in the quantum system, you look at whether it's a qubit 1 or qubit 0 to know whether the node belongs to one partition or the other. Here you look at the phases of the oscillators to know that, and we were able to get correct solutions both for the 4-node Mobius ladder as well as the 8-node Mobius ladder graph. This is 8-node Mobius ladder graph connected. So we got good solutions and everything was working well. So with that, I'll come to the end of the talk. So yeah, I'd like to thank my group, and which is kind of scattered right now across IIT Bombay and IIT Delhi. And I would like to thank the funding agencies listed here, and I would like to thank TIFR organizers for the professors at TIFR for organizing the talk and hosting me here and showing me their lab and like interacting with me. Thank you.
Yeah. Thank you, Debanjan, for taking us through the really emerging technologies, particularly from the perspective of hardware. Of course, we have been talking about the paradigms from in general as a computer science fields, but actually making devices and building and proving a point in terms of their performance. Of course, scaling up is always another ball game altogether. But it's very interesting that you took us through the real pieces of materials and how things are actually built. So it's very, very learning experiences. Yeah. So the talk is open now for more questions.
Hi, thank you. Could you please comment on what is the status in the industry? I mean, the development which is driven by the big chip makers like Intel and so in the neuromorphic computing direction. Are there any?
Also depends on what you mean by neuromorphic, because different people have different interpretations of neuromorphic. So Intel has its own neuromorphic solutions in the form of this Intel's Lohi chip, but that is not really a crossbar array architecture. That is like a digital chip only using traditional CMOS. The thing is, they play with the signals quite a lot. They claim it to be an asynchronous chip, where instead of having a global clock, they have some kind of local clocks, and they are implementing spiking neural networks on them. But that's still not a novel material-based crossbar array. But then the closest thing to a neuromorphic solution is probably the Intel's Lohi chip. So, and the way it works is you can enter into some kind of a partnership with Intel and get access to these Lohi chips, and you can run your algorithms there. But then that is neuromorphic in the sense that it's a asynchronous digital chip, is not still a novel material technology chip. Novel material wise, there are some startups in the US and some other countries probably which are building these memristor-based crossbar arrays, and they're trying to solve some problems with it. But like even like I would say that one major challenge with the neuromorphic communities right now is like they have not been able to find a killer application for neuromorphic. Like there are machine learning problems all over, and in most cases the regular AI implementation, ML implementation does the job, right? And neuromorphic will give you some energy benefit, but the amount of design changes that you need to make and the amount of innovation you need to make, is it worth it or not? I mean, is there one killer application for which the entire effort is worth it? The community is yet to find one. I mean, I'm saying it based on attending a lot of these conferences and hearing from other people who are working on this. So that is there. Potential applications that people have thought about this edge healthcare stuff. That is one. There are some people have tried to apply it, and the other places are like in space applications. People are thinking of whatever your energy budget is tight, basically. So that is what they're trying to think of using neuromorphic, right? There are advantages shown of neuromorphic on paper compared to the regular AI/ML, but is the advantage big enough to actually leverage like get something out of it? No, the answer is not very clear at this moment.
And just the follow-up question on your motivation of going to the Spintronic based systems as compared to most general, the memristor-based or something like that.
Yeah, RM. You mean RM, right?
Yeah. But, why particularly you went for this as compared to?
Well, the thing is, from a purely non-personal perspective, it is that RM devices have their own problems, like because you are trying to go up in the weights by creating oxygen filament, go down in the weight by destroying the oxygen filaments. So it's not a very smooth process, like creating and destroying things. On the other hand, domain wall is a very smooth motion. So you can get a much more linear behavior, much more well-controlled behavior. That is the technical answer. But this is talk of my research. I would say personally, for me, two things. One is RM is much more heavily explored. So for academics to make a footprint, it's easier to do something with Spintronic or something. The other thing is my background has been Spintronic device technology, not RM, right? That's another thing. Heavily?
Long-term stability in the application.
Yeah, endurance is also an issue. Stability is an issue. All these issues are there with RM. Spintronic has been known to be very high, have very high endurance. That's another thing. So the number of cycles that you can take an STT-MRAM and SOT-MRAM through is much more.
Are there any more questions?
So I had a couple of questions. One is this a technical one? In the last analog, the circuit, breadboard circuit you showed, what exactly is oscillating? Is it like a bunch of flip-flops flipping in?
Yeah, inverters. If you ring oscillators, right? So if you have an odd number of inverters, CMOS based inverters, if you have an odd number of them, connected in a loop.
So that's
That's
what,
what it
so
is.
it's basically each one is like a flip-flop, which is
Yeah.
going around and.
Yeah, the analog, yeah, transfer circuits, yeah,
Okay.
essentially.
And then, since in the previous part of your talk,
Yeah.
you were talking about this thing that if you only have one bit possibility in the synapse,
Mhm.
right, in terms of the weights, that you check that it does strain in some cases, and it
It
works.
does actually. One
Yeah.
bit update or one bit, the device having one bit.
No, the update,
The update being one bit, yeah.
Yeah.
It does strain, but
Is-
not in the complicated cases.
right. But is that, I mean, I'm not so sure, but isn't the brain's model says that it is sort of a bit, right? Each synapse will either fire or not fire and send the signal to the next
Yeah,
one.
yeah. So it's still a mystery how the brain does it. The question is, what you have built on hardware, can it really do it? And
Yeah.
there the answer is again, if the task is easy, the weight updating by. So imagine this, right? Your weight, you are at a certain value of weight, right?
Yeah.
And you are trying to get to the correct value, and they're like,
Yeah, no, I understand, because if each
If you
way
go
is
one
only,
step at a time,
the number of configurations is limited, so you may not find a solution.
yeah, if you go one
Yeah.
step at a time, imagine how much time it will take to get to the correct thing. So the answer is, if it's a network is simple, then it works. If the network is complicated, it does not work. Now then it's about what the goalpost, right? If you are, when I'm saying that it doesn't work, I'm talking about this convolutional, this kind of convolution networks. And these convolution networks are meant for handling very large images, very complicated images like C410 and all. These are complicated images. If you say that my application, final application of my neuromorphic computer is not to handle such complicated data, but much more simple data like this edge healthcare and all, then one bit would update is sufficient, right? So that is again depends upon what is your final application. So that is, so the way, I think the way to do neuromorphic research is you have to first think about the application, where do you want to apply it, gather a lot of data from that application, train your simulator on that application, and see if your hardware is good enough for it. Then you go and build it, right? But aiming for that moon, that okay, I'm just going to build a hardware which is going to work for, will be as good as a regular AI/ML algorithm right now, that I think is not very judicious.
Also, I guess that when there is a real development crossing roads, some existing little mature technology which is solving some real life problems, and here is another one, fundamentally a different, let us say, technology. At some stage, you will still see the so-called existing technology is outperforming, or at best, you may not actually see the advantage or quality factor that is coming in. But I guess when things move further, like the example you mentioned about how still some of the hardware-based, standard CMOS-based devices are performing and solving real problems, that is known. But I think when these things scale up and on the way you solve some of those issues, then that's where the real benefit keeps visible to application. But I'm not quite sure that the approach that you mentioned about finding applications and trying to kind of design or scale up technologies versus fundamentally looking at new technologies, which will find maybe potential applications as you go by. I know there's two ways one can keep on arguing about it, but maybe, well, okay. So it just
I've tried the latter route and I got a bit disillusioned. So I want to have that deciding of shifting to the forward.
It depends on whether you are a TIFR or IIT Bombay. So. Okay. So any other questions? Yes, there's one. Yeah. Can you please?
Is this one? Yeah. Just, I don't know if this question makes sense, but you said that one can simulate and check whether it's actually outperforms
the other
typical computer. So, like, what kind of a simulation do you perform on a traditional normal architecture, which suggests that your simulation is actually outperforming itself?
Nice question.
So again?
So this is one of your.
I get it. Okay. Towards the end, right?
I hear you.
No, towards the end, I know what you're talking about. You're talking about the time to solution and all that, right? I see. For example, this oscillator system, right? I think we can use this as an example, right? I'll drive home my point. If there's any fundamental fallacy in that argument, you just tell me, right? So suppose I have these equations and I say that these equations, like these oscillators, These are basically phases of the oscillators. That's phi 1, phi 2 up to phi n. And this is coupled equations, coupled differential equations, right? And these equations represent a physical system. And these coupled differential equations have their own time constant and the time dynamics, right? And I solve those coupled equations on a computer, right? Now, I'm never claiming that solving the coupled differential equation on a computer is taking faster than solving it some other way on a computer. What I'm saying is, suppose I've solved that thing on a computer and I'm looking at the solutions, how the phases are evolving over time, right? The time axis being in nanoseconds or picoseconds, depending upon what is the time scale I'm putting here. And I see that the time to solution, the time by which I'm getting the stable solution is not growing if I am having larger graphs. Versus I apply a classical approximation algorithm like a Gibbons-Williamson, and that thing, the time to solution clearly goes up, right? So a curve like this, right? But this time to solutions are clearly going up as a graph size versus a graph where it is not. The question is 20 node is less, and that's why I'm not making a bold comment about it. But if I go on 200 node, 500 node, and this goes up while this is flat or doesn't go up to that much, then I can make a claim. I don't think there's any, theoretical.
Yeah, I mean, I don't understand that part.
Yeah.
But yeah, that makes sense.
Yeah.
If answers tell you that the solution will reach in, say, 10 nanoseconds, but that calculation to show that can take 2 days.
2 days.
Actually, I thought that was his question.
Yeah.
So, very nice, Bhowmik. Thanks a lot for very, very interesting, and I think you took us to really some fields which many of us are absolutely unaware of. Thanks a lot, and we want to thank you, but want to thank you by giving this little memento to you.
Thank you so much.
Which is a memento of the asset colloquium that you gave on, which celebrated 40 years.
Thank you. Thank you so much.
Thank you. Thank you very much. So please join for a cup of tea.